Hello everyone. Today I will be talking about how to apply DC arc flash for photovoltaic systems into ETAP. To get started, I'd like to show you the sample PV system provided here, where we have a bunch of PV arrays combined into a combiner box, and then these combiner boxes all get added into this inverter cabinet. Now, the first item I'd like to show our new feature is how to model the PV array curves. To do this, let me show an example with this lone PV array 25. The first model I will show you is when you do not have a library defined in the PV editor. So when you go to the PV panel tab, you can define three specific data points. You can define the I short circuit, the V open circuit, and the maximum power point, which is the voltage and the current power point of the solar cell. So as you can see on this IV curve on the right, we have this I short circuit, the V open circuit, and this knee point, which is the maximum power. This plot also correlates to this PV curve, where you can see that this maximum power point is delivered where you see on that IV curve. And so this is called the linear three-point model. This is when you do not have a library defined, and you can tell when it's not defined when you don't have any heading in here. So the next two models I'll show you are very similar, that they're only created or shown when you select a specific library type. So in here, I'm going to select a specific model I made myself, the test single diode. And when I click OK, it will indicate what type of curve type on this section right here, curve type 1 diode estimation. And as you can see in the PV curves and the IV curves, the data points, there's many more data points, making this curve much smoother and more nonlinear. So this model is more accurate, and we prefer that you use either this model or the next model I will show you. So likewise, if I show you the third model, which is the 2 diode model, I created my own custom model here. I click OK. You'll see that the curves are very similar. They're actually practically the same, except maybe the 2 diode probably has higher current and efficiency output, but the curve look is very similar. So the next feature I'd like to show you or showcase is the irradiance curves, and how you can apply different PV generation irradiance curves into this editor. To do that, you would go to the PV array tab, and you will see that you have a table down below. So in this table, you can specify when this solar cell experiences a very high amount of sunlight, which is what this irradiance means. Or maybe you have a cloudy day and you maybe only experience half of the irradiance. You can also specify the ambient temperature that the cell is residing in. So maybe if it's in a very warm weather, you increase this temperature by, and this is in Celsius. And these two parameters will affect the PV curve shown on these two plots. So as an example, I'll do one where we are still basing on 1,000 watts per meter squared irradiance, but you will notice that there will be a second plot shown in the IV curve. So when I go here, you'll see there's a second orange plot. And notice how there's a slight difference between what the original plot was, which the original plot was based on 1,000 watts per meter squared with a base temperature of 25 degrees Celsius. Now, if I add another generation category of 500 to model a case when this is a cloudy day, you'll see that the irradiance has significantly dropped. You can see that the IV curve is like around half of what the base curve is. Now that we've shown you how to model the varying irradiances, I'd like to show you how you can select these irradiances in your arc flash study case. To do that, you would have to go to your study case, brown suitcase, click the source model tab, and in the bottom section, you'll see the short circuit contributions based on. So when you select the PV short circuit parameters, this means you're taking the base curve, that blue curve we saw earlier. But if you select the generation category option, you can select the varying irradiances based on that table we saw earlier. So in this example, I selected the irradiance to be at 500. So the study case will choose whatever irradiance or generation category irradiance was set here. Now that we have the PV array model and the irradiances set up in the PV array, the next thing I'd like to cover is how to input the data for the bus fault locations. So for example, in this combiner box, you can go to the AF parameters tab, and this is where you would input all of your dimensions of the box, as well as the distance between the conductor gap or the distance between the anode and the cathode. So the first existing feature we have already implemented is the enclosure reflectivity coefficients. So for each of, we have a variety of enclosure types or equipment types, enclosed equipment types. But the three main that you need to worry about or care about is the panel board, the low volt switchgear, and the medium volt switchgear. So based on the selection I make here, you'll see that the height, width, depth, as well as the A and K gets updated. But for the purposes of DC arc flash calculations, we only care about these A and K reflectivity coefficients. And these coefficients are correlated to this box size. So we have three equipments that have predefined values, and these are the ones that you want to use to match with your real life equipment to match with these box sizes. So for example, I select the low volt switchgear, you'll see that the box size has changed, as well as the A and K reflectivity coefficients that reflect that are based on this box size of 20 by 20 by 20. Likewise, the medium volt switchgear will have a bigger box size, and the reflectivity coefficients are also bigger. Next, I'd like to cover the conductor gap, the distance between the conductors. This is already an existing implementation in previous ETAPs, but this becomes very important in the next two new features we are going to implement in ETAP 22. And just to give a sneak peek, what I will be discussing will be the conductor erosion phenomenon, which are these new 3 added fields here, as well as the arc elongation effect, which is applied through this section added right here. Now that we have the PV array model set up, as well as defining the generation category, the next thing I'd like to cover is how to set up the arc flash study case method. So when we click the brown suitcase and go into the method tab, you will see that we have a variety of arc flash methods we can use to evaluate incident energy. Also, we also have an arc current determination method, either method 1 or 2, which we can use to determine how to calculate arcing current. For now, we will want to use the Stokes and Openlander method or the Pockert method. The reason being that these two methods were empirically derived, and so the actual lab tests were reflective of the actual energy equations. So these two methods go through an iterative process to solve for the arcing voltage, resistance, and arcing current. And with the iterative processes, we actually get a much more realistic incident energy result. On the other hand, The maximum power method is a theoretical assumption that the arc voltage is equivalent to 1/2 of the system voltage. And because this is a theoretical concept of applying the maximum power transfer theorem, we actually see that this is very unrealistic, where the energies are way too conservative. So on the other hand, the Stokes and Oppenlander and the Pocket methods, they actually calculate an arcing voltage that was only around 10 to 40% of the nominal system voltage. And this is why the incident energy released is not as high. That's why we will continue to choose the Stokes and Oppenlander method. Now, the reason why we want to select the method 2 for PV arrays is because PV arrays act as constant current injection sources, and so we need to use this method. The reason being that when you look at a PV array, right here, for example, and you see how what I was referring to about the arcing voltage and how it could range from 10 to 40% of the actual system voltage. Well, with that arcing voltage and going up to that arcing current, that will be the actual output of the PV array. And so, not like with the method 1 arcing current determination, we want to keep whatever that value we get from the PV curve. So in a typical case with method 1 arcing current determination, we would take this as the bolted fault current and then include arcing resistance to calculate an arcing current that's a little bit less than this line. But when we do method 2 determination, we assume that the arcing current is equivalent to the bolted fault current. And so the arcing resistance will actually be accounted for in the DC short circuit side of the calculation. But the main takeaway here is when you use method 2, we want the bolted fault current and the arcing current output from the PV array to be the exact same. Now that we have specified the PV array, the bus enclosure parameters, and the arc flash study case settings, let's run one study using the original settings I had set for the 500 irradiance. So in this case, remember how I selected in the source model at 500 and the Stokes and Oppenlander with using method 2 arcing current determination. You'll see that in this combiner box, I will get roughly 3 calories per centimeter squared for 2 seconds. Now, I also set up another scenario just to show you that the arc flash study case is choosing which irradiance generation categories to use. So in this scenario, I had set the generation category to use 1000 watts per meter squared. I run that study. You'll see that the energy almost doubles because the current almost doubles. Now, this is an overview of what ETAP has to offer with how to model PV arc flash. But the next 2 topics I'd like to show you are brand new features. The first feature I'd like to show you is in this study case. So when you go to the method tab again, you will see there is this option called Apply Elongation Effect. What this option does is ensures that whatever conductor gap you have set in the bus editor, it will mean that the arc length is not just predefined just to that conductor gap. Let's say we enable this option, apply. What this means is that when we go to here, when you're running an DC arc flash study, the conductor gap is not just limited to this distance of 20 millimeters. What actually occurs is the arc actually expands because of the heat and the ionization of the air. So the arc will start to curve and expand and lengthen. And to make sure that this setting is applied, we need to make sure that you have the arc elongation checkbox enabled here. We have some coefficients here similar to these reflectivity coefficients, You do not need to play around with these settings, as the default settings should be fine. But please make sure to have the arc elongation checkbox enabled if you want this phenomenon to occur. So when I had that enabled, let's see what happens when I run the arc flash study. Okay, so I'm going to rerun this particular case that had the 1000 irradiance, which was previously giving 6.4 calories. Let's see what happens when you apply arc elongation. So notice that the energy has increased to 9.967 calories. So when you apply the arc elongation effect, when you're increasing the arc length, you're going to increase the incident energy. The reason being that when you increase arc length, you're actually increasing the voltage across the arc. There was an equation developed that showed that there was a correlation between the arc length, and as it grows longer, that the arc voltage will also increase. And when you have this increase in arc voltage, your arc energy will also be increased. The next new feature I'd like to show you is the concept of conductor erosion. So as we saw earlier with the bus editor, how you can set a specific gap in between the conductors. Well, when an arc flash event happens, this conductor gap may actually increase in length because of a phenomenon called conductor erosion. And what happens is that when an arc flash happens, the high heat and the extremely high heat will actually vaporize the conductors. And so that's why we actually implemented three new fields, and these three fields are shown here in the erosion rate, cross-sectional area, and the total conductor length. So these two fields here are just explaining how fast the conductor will erode, as well as how big of a circumference or how much area does this conductor occupy. This third field here is the total conductor length that is exposed inside of the enclosure. So you can think of this, this conductor as kind of like a candlestick, and however much fault clearing time takes is however much fuel is available. So you can see this, let's say that this fault location takes 2 seconds to clear. But when you account for the conductor erosion phenomenon, the erosion may extinguish or eliminate all 305 millimeters of the exposed conductor, meaning that this fault location can only take 1 second to arc. And because it has no more fuel to burn, the arc will self-extinguish. So how do we apply this arc erosion phenomenon? To do that, you will go into the study case, go to the method tab, and then apply the consider erosion. So this will allow you to see if the conductor gap will get increased based on its vaporizing and melting of the conductor. But this option, limit FCT based on conductor erosion time, this is the example I was saying about the candlestick, about if the conductor gets completely eroded, then your FCT will be limited based on the time that the conductor gets eroded. So let's, for example, enable this option and see what happens to the DC arc flash results. Okay, so I'm going to run the study here. And then you'll see this conductor, the gap in between conductors, with this available conductor exposed length. It took only 12 milliseconds to completely demolish this conductor. And so therefore your energy has drastically reduced. Just so that you also have a quick back of the hand calculation to check, you may still also use the power calculator, which is an additional program available when you purchase the DC Arc Flash license, and we have the same features implemented in the Method tab. So for example, you will need to select the iterative methods, which are the Stokes or Packard. And now you should see in the Method tab, now you have the option to apply conductor erosion or apply the arc elongation or the arc length increasing effect. So in this calculator example, we can just play around with the settings just to show you how these options affect the actual final results. So in this case, I will have, based on these given set of parameters, I get an energy result of 13 calories. Now, to go back to the arc elongation effect, remember how I mentioned how the arc length correlates to the increase in the voltage of the arcing voltage. And with the increase in the arcing voltage, you'll see that the energy increases. So enabling this, applying the arc elongation effect, you see how previously it was 115, it changed to 165. And our previous energy of 13 calories has changed to 18 calories. Now let's say we want to apply both of the arc elongation and the conductor erosion. So when we enable this, you may notice that this calculation warnings message will tell you if the amount of exposed conductor has completely eroded. Okay, so when I enabled that, in the calculator, it told me that the erosion time was set to 0.273 seconds. So instead, the calculator will use the 0.273 seconds to calculate the final energy. Just as a recap to go over all the new features we've implemented into DC Arc Flash. So the first item was the concept of the PV generation category based on irradiance, and how you could define the irradiances in the PV array tab and set your irradiances based on the generation categories, and how you could select in the study case source model tab, you can select which generation category you want to use. Also, the second item that we introduced was the concept of arc elongation, which just means that when the arc flash event happens, the arc will not just be limited to the distance in between the conductor gaps. And so the arc will start to increase in length because it is not just limited in that distance, it could just start to curve and lengthen around the electrodes. The last concept we also had discussed was the conductor erosion phenomenon, when the conductor can act like a candlestick melting away, where if the conductor erodes so quickly that it could actually limit the amount of FCT and extinguish the arc itself. Thank you for joining me in discussing all of the new features for DC Arc Flash.